distances between stars are vast, almost unimaginably vast. The nearest star system, Proxima Centauri, is over 4.24 light-years away. Even at the speed of our fastest spacecraft, it would take tens of thousands of years to reach it. So the question arises, is interstellar travel even possible? And more specifically, could concepts like the warp drive ever let us break the cosmic speed limit set by the speed of light? The distances between stars are so vast that even traveling at unimaginable speeds with today's technology would take thousands of years to reach the nearest solar system. Proxima Centauri, just over 4 light-years away, might seem close on a cosmic scale, but with our fastest rockets, it would take more than 17,000 years to get there. That reality makes conventional space travel impractical for interstellar exploration. Concepts like nuclear or ion propulsion extend range and efficiency, but even these would be painfully slow for humans hoping to reach other stars within a lifetime. This is why the idea of a warp drive captures the imagination so strongly. A warp drive doesn't let a spacecraft move faster than light in the usual sense. Instead, it manipulates spacetime itself. The ship sits inside a bubble, a region of spacetime that contracts in front of it and expands behind it, effectively carrying the vessel faster than light relative to distant observers without violating the local speed limit set by Einstein's theory of relativity. This means that the ship itself isn't traveling through space at faster than light speed. Space is moving beneath it. The mathematics behind this idea was first formalized by physicist Miguel Alcubierre in the 1990s, and it showed that, in theory, general relativity permits the formation of such a bubble. The physics is elegant, but the practical challenges are enormous. Early calculations suggested that creating a warp bubble would require more energy than exists in the observable universe. Later refinements reduced this to an amount equivalent to a few hundred kilograms of mass converted directly into energy, still far beyond anything humanity can produce or control. To sustain a warp bubble, some form of exotic matter with negative energy density is required. Negative energy is unlike anything we can harness today. Certain quantum phenomena, like the Casimir effect, hint at its existence in minuscule quantities, but producing and stabilizing enough of it to bend spacetime on a starship scale remains purely theoretical. Even if exotic matter could be found or manufactured, controlling it safely poses challenges we cannot yet imagine. Any slight imbalance in the warp bubble could collapse spacetime around the ship, with catastrophic consequences. There are also questions about how a warp bubble would interact with the rest of the universe. Would it generate dangerous radiation, distort neighboring stars, or destabilize planetary orbits? The unknowns are immense, and yet the theoretical possibility is enough to drive scientists and dreamers to continue exploring it. While the warp drive captures our imagination, other interstellar propulsion methods may be more achievable in the nearer term. Fusion-powered rockets, for example, could generate incredible speeds by fusing isotopes of hydrogen, producing energy thousands of times more efficient than chemical rockets. Antimatter propulsion is another concept where matter and antimatter annihilation releases enormous amounts of energy, pushing spacecraft to a significant fraction of the speed of light. Both technologies are far from practical today, requiring advances in energy production, containment, and engineering. Light sails offer a different approach, harnessing radiation pressure from lasers or the sun to gradually accelerate a spacecraft to relativistic speeds. Projects like Breakthrough Starshot propose tiny, ultralight probes propelled by ground-based lasers to reach Alpha Centauri in about 20 years. While these probes are small and cannot carry humans, they demonstrate that interstellar travel may be achievable with innovative engineering long before warp drives become practical. Interstellar travel also forces us to confront the consequences of relativity. Even at a significant fraction of light speed, time dilation becomes a factor. For astronauts traveling near the speed of light, time would pass more slowly on the ship than for people back on Earth. A journey that seems like decades for the travelers could span centuries on Earth. this reality has profound implications for colonization, communication, and the continuity of human civilization across the stars. The energy requirements for any interstellar journey are staggering. Propulsion systems capable of even a fraction of light speed demand amounts of energy that challenge our understanding of practical engineering. Beyond propulsion, life support, shielding from cosmic radiation, and navigation across light years of space must be accounted for. Even the smallest mistakes over such distances could have fatal consequences. Interstellar travel is not just a problem of physics, it is an engineering, biological, and logistical challenge on an epic scale. Despite these obstacles, theoretical and experimental work continues. Researchers investigate warp drive metrics, simulate space-time manipulations, and explore potential energy sources that could make such travel feasible. Each study helps us understand the limits of physics and the possibilities for the future. Even if humanity never achieves a full warp drive, the ideas inspire technological innovation and push the boundaries of what we consider possible. Beyond technology, interstellar travel raises profound philosophical and societal questions. What would it mean for humans to become a multi-star species? How would culture, identity, and governance evolve when separated by light years? Could societies remain connected across centuries-long voyages? Or would each colony develop independently, creating entirely new civilizations? The journey itself becomes as much a human and cultural challenge as a scientific one. Even if humans manage to leave the solar system, choosing where to go is critical. Not every star has planets suitable for life, and most are far less hospitable than Earth. Astronomers have discovered thousands of exoplanets, and some appear to have conditions that might support life or human habitation. Among the closest is Proxima Centauri b, a planet orbiting the nearest star which lies within the so-called habitable zone where temperatures could allow liquid water. Other nearby targets include planets in the TRAPPIST-1 system, a compact group of Earth-sized worlds roughly 40 light-years away, and planets around Tau Ceti, which may offer stable orbits and moderate climates. These worlds are not paradise. They face challenges like intense radiation, low gravity, and uncertain atmospheres, but they represent potential footholds for humanity's first steps beyond the solar system. Planning a human mission to these stars requires considering survival for decades, centuries, or longer. Generational ships may carry thousands of people, along with complete ecosystems, food supplies, water recycling, and energy systems capable of sustaining life indefinitely. In such a mission, every system must be redundant and self-repairing. Mechanical failures, crop failures, or unexpected radiation events could jeopardize generations of travelers, making reliability and monitoring paramount. Autonomous systems and artificial intelligence will likely play a central role in interstellar travel. AI could maintain life support, monitor structural integrity, adjust propulsion systems, and manage energy distribution without human intervention. Autonomous robots could handle repairs, explore potential landing sites, and even produce new materials from harvested asteroids or comets encountered along the journey. Essentially, the crew might rely on intelligent companions and systems that manage the voyage while humans focus on exploration, scientific research, and cultural life within the ship. Time, distance, and isolation force humans to confront the meaning of existence on a cosmic scale. Colonists aboard an interstellar ship may never see Earth again, and communication delays will stretch to years as they travel farther from the sun. Humanity must consider how social structures, education, governance, and culture evolve under these conditions. Will colonies retain Earth traditions, or will new societies emerge adapted to the realities of space? Interstellar travel is not only a test of physics and engineering but a profound experiment in sociology and philosophy. The risks of such voyages are enormous, but the potential rewards are transformative. Reaching a new star system would ensure the long-term survival of humanity if Earth faced catastrophic events, opening access to new resources, knowledge, and experiences. It would also inspire generations, reminding us that exploration is part of our nature. The dream of interstellar travel, like the dream of warp drives or terraforming distant planets, represents humanity's desire to transcend limits, explore the unknown, and take responsibility for our destiny in the universe. Even if humans never reach other stars within our lifetimes, pursuing interstellar travel drives innovation on Earth and within the solar system. Research into propulsion, energy storage, life support, and autonomous systems benefits lunar bases, Mars colonies, and deep space probes. Experiments in extreme environments teach us how to live sustainably and adaptively. The pursuit of interstellar knowledge, even indirectly, enhances our capacity to thrive at home while preparing us for the farthest reaches of space. Long-term colonization of other star systems is an endeavor that could span centuries or even millennia. Early colonies would prioritize survival, stable energy sources, reliable life support, and sustainable food production. Over time, as technology improves and populations grow, colonies could expand, terraform local environments, and develop complex societies. Eventually, humanity might establish networks of star systems, each with unique cultures, ecosystems, and economies, yet linked by shared knowledge and history. The ethics of colonizing other worlds must be carefully considered. While planets that appear barren might seem open for human habitation, we cannot be certain that microbial life or other ecosystems do not exist. Colonization could inadvertently destroy life we cannot detect, disrupting environments that have evolved over millions of years. Responsible interstellar exploration requires weighing our survival against the potential impact on unknown ecosystems, emphasizing stewardship as much as ambition. Psychological and societal adaptations are critical for long-term interstellar life. Generations of humans living in confined habitats or on distant planets face isolation, limited social contact, and extreme environments. Maintaining mental health, social cohesion, and cultural continuity requires careful planning. Education, recreation, and governance must be designed to support populations isolated from Earth for decades or centuries. Social structures may evolve in unexpected ways, blending Earth traditions with the practical demands of survival in new worlds. Interstellar humans must also grapple with the philosophical implications of their existence. Living across light years transforms how we perceive time, space, and identity. Colonists may never see Earth again, and communication with family, friends, or governments could take years or decades. The idea of home expands beyond a planet to a system, a habitat, or even a generation-long journey through the cosmos. Humanity's understanding of itself, of its place in the universe, and of its responsibility to future generations must evolve alongside its technological achievements. The ultimate significance of humans spreading among the stars is profound. It represents a species willing to take responsibility for its survival while engaging with the universe in a conscious, deliberate way. Every settlement, every interstellar mission, and every technological advancement is a testament to curiosity, resilience, and the drive to transcend limitations. By reaching other stars, humans test the boundaries of physics, engineering, and imagination, but also the boundaries of morality, society, and culture. Humanity becomes not just an Earth species, but a cosmic one with a stake in the life of the universe itself. The dream of interstellar travel reminds us that exploration is inseparable from identity. Just as our ancestors crossed oceans to discover new continents, we now look to the stars to extend the frontier of civilization. The challenges are vastly greater, the distances are incomprehensible, the energy required immense, and the risks extreme. Yet their ambition is the same: to understand, to explore, and to endure. Every theoretical breakthrough, every experiment in propulsion, every probe sent to a distant star teaches us something about the universe and about ourselves. Ultimately, interstellar travel is about hope. It is about imagining a future where humans survive beyond Earth, where knowledge and culture thrive across systems, and where curiosity drives progress. Even if warp drives remain theoretical, even if the first human explorers are centuries away, the pursuit itself inspires, educates, and transforms. It encourages collaboration across generations and nations, pushing humanity to innovate, adapt, and dream beyond conventional limits. Interstellar travel challenges us to think in ways that stretch comprehension. It demands consideration of energy, time, and life on scales larger than any single human or civilization. It asks us to balance ambition with ethics, risk with survival, and imagination with pragmatism. Preparing for journeys to the stars is not simply a scientific or technological challenge, it is a deeply human one, calling on ingenuity, courage, and foresight. By striving to reach other stars, humanity affirms its place in the universe, not as passive observers but as active participants. The dream of warp drives, multi-generational ships, and distant colonies symbolizes the desire to overcome limits, explore the unknown, and ensure the continuity of life. Every calculation, every experiment, and every mission, even if it falls short, contributes to this grand vision. Interstellar travel may take centuries or millennia to achieve fully, but the journey itself of knowledge, culture, and human ingenuity transforms us today, shaping who we are and what we can become. As we consider the possibility of warp drives and other advanced propulsion methods, it becomes clear that interstellar travel sits at the edge of human understanding. Warp drives, with their elegant manipulation of space-time, remain largely theoretical, requiring exotic matter and energy levels far beyond anything we can currently produce. Even so, exploring these ideas expands our knowledge of physics, revealing new insights about gravity, relativity, and the structure of the universe. Alternative propulsion methods, like fusion engines, antimatter drives, and light sails, offer more immediate paths toward interstellar exploration, though they too present enormous engineering and energy challenges. Every concept, experiment, and calculation contributes to a broader understanding of what is possible, preparing humanity for journeys we may one day take. Interstellar travel is not merely a technical challenge, it is a human one. It forces us to ask fundamental questions about our survival, our ethics, and our place in the cosmos. How do we preserve life and culture across generations? How do we explore responsibly without harming alien worlds we may encounter? How do we maintain hope and purpose during journeys that span decades or centuries? These questions are as important as the equations describing warp bubbles or the designs of multi-generational ships. They remind us that exploration is inseparable from imagination, morality, and vision. The pursuit of interstellar travel connects science, engineering, and philosophy. It drives innovation in energy, materials, and life support systems while inspiring cultural and ethical reflection. It challenges humans to think beyond the immediate, to plan for civilizations that may last centuries, and to imagine futures that stretch across light years. Every step we take toward understanding faster-than-light travel or designing starships shapes the way we think, the way we live, and the way we dream. Ultimately, the quest to reach the stars is a story of hope, ambition, and resilience. It reflects the deepest human desire to explore, to survive, and to expand our presence across the universe. Even if warp drives remain theoretical, even if the first humans to visit another star are centuries away, the vision itself transforms us. It encourages curiosity, innovation, and courage, inspiring generations to look up at the night sky and imagine possibilities beyond what we know. Segment 6 closes with the understanding that interstellar travel is both a practical and philosophical frontier. It is a challenge that blends physics, engineering, ethics, and imagination. It asks us to consider what it means to be human on cosmic scales and to envision a future where humanity thrives not only on Earth but across the stars. The dream of warp drives, fusion engines, and generational starships may seem distant today, but the pursuit of these dreams drives science, shapes culture, and fuels the ambition that defines our species. As we continue to study the cosmos, develop technology, and expand our understanding, the stars await. They remind us that the universe is vast, full of challenges, mysteries, and opportunities. They invite us to push limits, to imagine boldly, and to embrace the unknown. Interstellar travel may be the ultimate human endeavor, combining intellect, courage, and vision. It is the story of humanity reaching outward, not only to survive, but to explore, understand, and become something greater than ourselves. Each step forward, each theoretical breakthrough, and each technological advance brings us closer to a future where humans may walk among the stars, fulfilling the ancient desire to explore, survive, and thrive in a universe of infinite possibilities. Building bridges to the stars, space elevators, and megastructures. Imagine a structure so tall it reaches from the surface of Earth all the way into space, a bridge between our planet and the stars. This is the idea behind a space elevator, one of humanity's most ambitious engineering concepts. At its core, a space elevator is a tether anchored to the equator of Earth and extending upward beyond geostationary orbit, where a counterweight keeps it taut. Vehicles, called climbers, could ascend this tether to transport cargo, and potentially humans, directly into orbit without rockets. The concept seems almost like science fiction, but it is grounded in real physics and materials science. The potential advantages of a space elevator are staggering. Rockets are expensive, complex, and require massive amounts of fuel to escape Earth's gravity. A space elevator could drastically reduce the cost of lifting materials into orbit, enabling more frequent launches, large-scale construction in space, and even faster deployment of satellites. Imagine building vast orbital habitats, solar power stations, or interplanetary ships with far less energy and expense than current rocket launches allow. Space elevators could transform space travel from a rare, expensive endeavor into something more routine and accessible. Of course, building a space elevator is an extraordinary challenge. The tether must be both incredibly strong and light, far beyond the capabilities of steel or any conventional material. Engineers propose advanced carbon-based materials like carbon nanotubes or graphene, which theoretically have the necessary tensile strength. Yet producing a tether thousands of kilometers long with consistent quality and durability remains beyond our current manufacturing abilities. Environmental factors such as storms, high winds, and even space debris create additional obstacles. A single collision with a satellite or micrometeoroid could sever the tether if it is not protected by careful design and monitoring systems. The counterweight at the far end of the tether is another engineering hurdle. It must be massive enough to maintain tension but light enough to be practically deployed. Some proposals suggest placing an asteroid in orbit as the counterweight, while others imagine using large artificial structures. Balancing the tether under the influence of Earth's rotation, gravity, and orbital dynamics is an engineering puzzle that pushes materials science and physics to their limits. Despite the challenges, the idea of a space elevator has inspired researchers and space agencies for decades. Japan, Russia, and private companies have all studied potential designs and feasibility. Some concepts focus on near-term partial elevators that reach tens of thousands of kilometers into the atmosphere, offering smaller but still significant reductions in launch costs. Others imagine full-scale elevators stretching beyond geostationary orbit, capable of supporting industrial-scale operations in space. Space elevators could also serve as platforms for other megastructures. For instance, orbital rings, tethered habitats, and solar power stations could be constructed directly in space using materials delivered by the elevator. These megastructures could support vast human populations, provide energy to Earth, or serve as launch points for missions deeper into the solar system. In many ways, the space elevator acts as a spine, enabling the construction of the skeleton of a spacefaring civilization. The idea extends even beyond Earth. A space elevator on the moon would be far easier to build because lunar gravity is only 1/6 of Earth's, and there is no atmosphere to contend with. Similarly, Mars could host its own elevator, opening the door to regular transport of materials and people between the surface and orbit. These structures could serve as stepping stones for colonizing other planets, linking planetary surfaces to orbital habitats, research stations, and interplanetary spacecraft. Engineering a space elevator is not only about material science, it requires precise understanding of orbital mechanics, energy transfer, and structural dynamics. Climbers must ascend smoothly without creating vibrations that could destabilize the tether. Energy could be transmitted via laser or electrical systems, powering the climbers as they travel thousands of kilometers. Monitoring systems must constantly detect debris, weather, and material stress to prevent catastrophic failures. The level of coordination between robotics, automation, and human oversight is unprecedented in engineering history. The promise of megastructures doesn't stop with elevators. Concepts like orbital habitats, Dyson swarms, and artificial rings envision humanity reshaping the space environment to support life, industry, and energy production. Dyson swarms, for example, involve constructing thousands or millions of satellites around the sun to capture its energy. This would provide nearly unlimited power for humanity's needs, enabling massive industrial activity in space without depleting Earth's resources. Constructing these megastructures would require a new industrial base in orbit, capable of mining asteroids, refining materials, and assembling large-scale structures in microgravity. Space elevators could provide the initial transport needed to bring resources and equipment into orbit efficiently. Once established, orbital factories could produce components for further expansion, creating a self-sustaining cycle of construction and habitation. The engineering, economics, and logistics of such projects are mind-boggling, yet they highlight the potential future of human civilization. Megastructures could not only transform how we access and use space but also redefine our relationship with energy, resources, and population growth. They could allow humanity to spread across the solar system without being constrained by the limitations of earthbound infrastructure, offering a vision of abundance and sustainability on a cosmic scale. Beyond the practical, these structures push the boundaries of imagination. A functioning space elevator or Dyson swarm would be visible from Earth, a testament to what a civilization can achieve with ingenuity and ambition. They are symbols of a future in which humanity no longer dreams small, in which we use our knowledge, creativity, and engineering to reach beyond our planet, shaping space itself as a habitat and resource. Several designs have been proposed for space elevators, each with unique features and challenges. One popular concept is the climber-on-tether model, where robotic or human-piloted vehicles ascend the tether from the equatorial base station to geostationary orbit and beyond. These climbers could carry cargo, satellites, or eventually humans, powered by electrical cables embedded in the tether or by wireless energy transfer from lasers. Another design proposes a ribbon-like tether that can adjust tension and orientation in response to environmental changes, such as high-altitude winds or tidal forces from the moon. Some futuristic models even imagine multiple parallel tethers, increasing capacity and redundancy while reducing the risk of catastrophic failure. Safety is a major concern for any megastructure in space. Space elevators would be exposed to storms in the upper atmosphere, lightning strikes, high winds, and space debris traveling at tens of thousands of kilometers per hour. Even small pieces of debris could puncture or weaken a tether. To counter these risks, engineers propose using shields, automated repair drones, and constant monitoring systems. The tether itself could be designed with multiple layers of redundant materials, allowing sections to fail safely without compromising the entire structure. The base stations would need lightning protection, vibration dampening systems, and rapid evacuation procedures in case of emergencies. Space elevators also open the door to entirely new kinds of orbital megastructures. Orbital rings, for example, are enormous rotating bands around a planet or moon, designed to provide artificial gravity for habitats and industrial centers. Solar power satellites could be built in orbit and transmit energy back to Earth via microwave or laser beams, providing clean, continuous power. Dyson swarms collections of thousands or millions of energy-collecting satellites around the Sun represent another level of ambition, allowing humanity to harness nearly the full output of our star. Each of these projects depends on reliable access to orbit, something a space elevator could provide, and could fundamentally alter humanity's energy and resource base. The logistics of constructing orbital megastructures are staggering. Materials would need to be mined from asteroids, the moon, or other celestial bodies to avoid the high cost of lifting everything from Earth. Robotic assembly crews in orbit could fabricate massive components, which would then be transported to their final positions using automated systems or climbers on the space elevator. Over time, humanity could develop self-sustaining habitats in orbit, reducing pressure on Earth's environment and enabling the expansion of civilization into space. The societal impacts of space elevators and megastructures would also be profound. With drastically reduced launch costs, space could become accessible to more nations, companies, and research organizations. This democratization of space could spur technological innovation, international collaboration, and new industries. However, it also raises questions about governance, property rights, and security. Who controls access to the elevator or the orbital infrastructure? How do we prevent accidents or conflicts in orbit? Solving these issues requires global cooperation and new legal frameworks to manage humanity's expanding presence in space responsibly. Beyond Earth, space elevators could be built on other worlds to support exploration and colonization. A lunar elevator would be far easier to construct than an Earth-based one because of the moon's lower gravity and lack of atmosphere. Such a structure could facilitate the transport of materials from the lunar surface to orbit, supporting lunar mining operations, scientific research, and space-based solar power stations. Mars could also host a space elevator connecting the surface to orbit to assist with colonization efforts, interplanetary launches, and resource distribution. These extraterrestrial elevators would serve as critical infrastructure for humanity's expansion into the solar system. The vision of space elevators and megastructures also inspires the imagination. Seeing a tether stretching from Earth into the sky, or an orbital ring supporting thousands of habitats, would be a visible reminder of human ingenuity and ambition. These structures symbolize our ability to overcome limits, to turn the void of space into a domain we can inhabit and utilize. They remind us that our species is capable of building on scales and with precision that were once unimaginable. Ultimately, space elevators and megastructures represent the bridge between Earth and the wider cosmos. They are tools for exploration, industry, and survival, enabling humanity to leave the planet more efficiently and sustainably. They challenge our engineering, physics, and resource management skills while also reshaping our relationship with space, energy, and society. If realized, they could mark the first step toward a truly spacefaring civilization where humans live, work, and thrive beyond Earth on a scale never before imagined. Segment 7 closes with the understanding that the universe is not a static backdrop, but a domain that humanity can gradually explore, inhabit, and transform. Space elevators, orbital habitats, Dyson swarms, and other megastructures are the first tangible steps toward this future. They combine practicality, ambition, and imagination, demonstrating what is possible when science, engineering, and vision work together. By pursuing these projects, we prepare ourselves not only for life beyond Earth but for the challenges and opportunities of a truly spacefaring civilization where human ingenuity can flourish on a solar system and eventually a galactic scale. Asteroids mining the future of space. Asteroids might seem like tiny, distant rocks drifting through space, but they could hold the key to humanity's future beyond Earth. These space rocks are remnants from the formation of the solar system, containing a wide variety of metals, minerals, and even water. Mining asteroids could provide resources that are rare or expensive on Earth, enabling space exploration, industrial activity in orbit, and even the development of new technologies. Instead of relying solely on Earth for materials, humans could use these floating treasure chests as building blocks for a spacefaring civilization. The types of asteroids vary greatly, and so do the resources they contain. Some are metallic, rich in iron, nickel, and cobalt, which are critical for building spacecraft satellites and orbital infrastructure. Others are carbonaceous, containing water, organic compounds, and rare elements like platinum or gold. Water is especially valuable because it can be split into hydrogen and oxygen to create rocket fuel or provide life support for astronauts. In effect, mining asteroids turns these space rocks into floating factories, supplying everything from raw materials to fuel, reducing the need to lift heavy cargo from Earth's surface. Accessing asteroids is not simple. Many are located in the asteroid belt between Mars and Jupiter, while others have orbits that bring them closer to Earth. Scientists look for near-Earth asteroids because they are easier to reach with current spacecraft technology. Even then, traveling to and landing on an asteroid requires precise navigation, propulsion, and robotics. Many asteroids rotate quickly or have irregular shapes, making landings tricky. Engineers must design spacecraft that can attach to or hover near these bodies while extracting materials without being thrown off by the asteroid's low gravity or uneven surface. Several mining methods have been proposed, each with its own advantages and challenges. One approach is robotic excavation, where automated systems drill, scoop, or blast material from the asteroid and transport it back to orbit or Earth. Another method involves using inflatable or magnetic collection systems that gather small particles and dust from the asteroid's surface. Some concepts even suggest melting or vaporizing parts of the asteroid to capture valuable metals or water, turning the rock itself into a processing plant. Each method requires careful planning because a mistake could damage the spacecraft or send debris into dangerous trajectories. The economics of asteroid mining are complex but promising. Platinum group metals, gold, and other rare elements could be worth billions if delivered to Earth or used in orbit. Water and fuel in space are even more valuable because transporting them from Earth is extremely costly. By creating a supply of materials in orbit, asteroid mining could support orbital manufacturing, construction of large habitats, and space elevators. In effect, asteroids could provide the raw ingredients for building human civilization in space, making projects that now seem impossible more feasible. Challenges extend beyond engineering and economics. Legal and ethical questions arise about who owns an asteroid, how resources can be claimed, and how conflicts between nations or companies are managed. International space law currently allows for the use of resources, but enforcement and regulation are still developing. Cooperation between nations and private companies will be essential to prevent disputes, ensure safety, and maintain sustainable practices in space. The goal is to make asteroid mining not just profitable, but also responsible and equitable. Asteroid mining could also support deep space exploration. Water extracted from asteroids can be converted into fuel, allowing spacecraft to refuel far from Earth. This would reduce mission costs and enable longer voyages to Mars, the outer planets, or even beyond the solar system. Materials like metals and silicon could be used to build habitats, spacecraft, and solar power arrays directly in orbit, bypassing the limitations of Earth-based manufacturing. By tapping into asteroid resources, humanity gains the ability to operate independently of Earth, creating a self-sustaining presence in space. Several companies and space agencies are already exploring asteroid mining. Missions like NASA OSIRIS-REx and Japan's Hayabusa 2 have visited asteroids, collected samples, and returned them to Earth. These missions provide invaluable information about asteroid composition, surface conditions, and behavior, laying the groundwork for future mining operations. Private companies are developing spacecraft and robotic systems capable of extracting materials, and plans for near-term demonstration missions are underway. While large-scale mining may still be decades away, the groundwork is being laid today. The potential societal impact of asteroid mining is enormous. On Earth, it could supply rare metals for electronics, renewable energy technologies, and medical devices, reducing scarcity and environmental strain. In space, it enables the construction of habitats, solar power stations, and infrastructure needed for long-term human presence. Asteroid mining is not just about collecting rocks, it's about creating the foundations of a new economy and a new way of life in space. Asteroids are also scientifically valuable. Studying them can teach us about the early solar system, the formation of planets, and even the origins of water and organic molecules that led to life on Earth. Mining operations could double as research missions, combining economic activity with scientific discovery. In this way, humanity benefits both practically and intellectually, learning about our place in the cosmos while preparing to expand into it. Ultimately, asteroid mining represents a crucial step toward making humanity the multiplanetary species. By turning these wandering rocks into resources, we gain materials, fuel, and knowledge necessary for life beyond Earth. Space elevators, orbital factories, and interplanetary missions all depend on reliable access to raw materials, and asteroids may provide the most abundant and accessible supply. In the coming decades, asteroid mining could shift from a concept in science fiction to a practical cornerstone of our future in space. Mining asteroids requires creative solutions because these rocks are small, irregular, and have almost no gravity. Traditional mining techniques used on Earth, like digging tunnels or operating heavy machinery, are impractical. Instead, engineers have designed specialized robotic systems. Some spacecraft could use harpoons, drills, or scoops to extract material from the surface, while others might employ vacuum-like collection systems to capture loose dust and small rocks. These methods take advantage of microgravity, allowing spacecraft to gently maneuver around the asteroid while slowly gathering resources without disturbing the object's rotation or trajectory. Another proposed technique is in situ resource processing. This involves processing asteroid material directly in space, rather than returning it to Earth. For example, water could be extracted and split into hydrogen and oxygen for fuel, while metals could be refined for construction or electronics. By processing resources in orbit, spacecraft avoid the massive energy cost of lifting materials from the surface of Earth. In effect, the asteroid becomes both a resource and a factory supplying fuel and materials for space operations, industrial habitats, and even large megastructures like orbital rings or solar power satellites. Several missions have already paved the way for asteroid mining. NASA OSIRIS-REx mission visited the near-Earth asteroid Bennu, collected samples, and returned them to Earth in 2023. The Japanese mission Hayabusa 2 similarly visited the asteroid Ryugu, returned samples, and provided critical data on surface composition and structure. These missions teach scientists how to land, collect, and return materials safely, while also revealing what resources are available and how they might be extracted. Future missions may test robotic mining techniques in orbit or on asteroid surfaces, laying the groundwork for full-scale industrial operations. Private companies are increasingly entering this field, aiming to make asteroid mining commercially viable. Some plan to launch small prospecting spacecraft to identify valuable asteroids, mapping resources like platinum, rare earth elements, and water. Others envision fleets of autonomous mining robots capable of extracting materials continuously, processing them in orbit, and transporting refined products to space stations, lunar bases, or even Earth. The combination of private innovation, government support, and international cooperation could accelerate asteroid mining from concept to reality within the next few decades. The economics of asteroid mining hinge on both the value of the resources and the cost of accessing them. Rare metals such as platinum, palladium, and gold could be worth billions if returned to Earth, while water in space is even more valuable, supporting fuel production and life support. By establishing a supply chain that operates in orbit, humanity can reduce dependence on Earth-based materials, enabling large-scale projects in space that would otherwise be prohibitively expensive. Over time, asteroid mining could shift the economics of space, making exploration and colonization financially feasible for both governments and private enterprises. Legal and ethical questions also come into play. International treaties, like the Outer Space Treaty of 1967, state that space is the province of all humankind and prohibit national claims on celestial bodies. However, the treaty allows for the use of resources, which has led countries like the United States and Luxembourg to pass laws enabling companies to own extracted materials. Questions remain about fair access, environmental impact, and long-term sustainability. The development of asteroid mining will require clear regulations, international agreements, and responsible practices to avoid conflict and ensure the benefits are shared. Asteroid mining could also have major implications for interplanetary travel. Water extracted from asteroids can be converted into rocket fuel, enabling spacecraft to refuel mid-journey. This reduces the mass a mission must carry from Earth and extends the range of human exploration. Metals and other materials can be used to build spacecraft, habitats, and industrial infrastructure directly in space. By creating a self-sufficient supply chain, humanity can operate far from Earth, whether on Mars, the Moon, or deep space missions to the outer planets. In addition to practical benefits, asteroid mining is scientifically valuable. Asteroids are time capsules, preserving materials from the earliest days of the solar system. Mining operations can also serve as research missions, revealing the composition, structure, and history of these primordial rocks. Studying asteroids helps us understand the formation of planets, the origin of water and organic molecules, and even the conditions that led to life on Earth. This dual-purpose economic and scientific makes asteroid mining one of the most exciting frontiers of space exploration. The long-term vision for asteroid mining is ambitious. Over decades, humanity could establish orbital mining stations, fleets of robotic extractors, and processing facilities. Water and metals could supply orbital habitats, space elevators, megastructures, and interplanetary missions. The solar system's resources, once inaccessible, would become part of a network supporting human expansion, energy production, and industrial activity. In this vision, Earth remains home, but the solar system becomes a living, working environment, and asteroids act as stepping stones for a sustainable presence in space. Ultimately, asteroid mining represents more than just resource extraction. It represents a shift in humanity's relationship with space. These once distant rocks could supply the building blocks for energy, infrastructure, and life itself, making ambitious projects like space elevators, orbital habitats, and interstellar missions possible. By learning to mine and process asteroids responsibly, humanity gains the ability to thrive beyond Earth, building a future where space is not a frontier we merely explore, but a realm we inhabit, utilize, and transform. As asteroid mining advances, engineers envision increasingly sophisticated techniques to maximize efficiency and safety. One concept is autonomous robotic fleets, swarms of small, intelligent mining drones that can coordinate their work without direct human supervision. These drones could drill, scoop, or vaporize materials, sorting valuable metals and water on site. By using swarm intelligence, multiple robots can operate simultaneously on irregular or rotating asteroids, reducing mission time and increasing yield. Automation is critical because the distances involved make real-time human control difficult. Even light-speed delays can be several seconds for near-Earth asteroids and much longer for those farther away. In-orbit processing is another key innovation. Instead of returning raw material to Earth, spacecraft could refine and assemble components directly in orbit. Water extracted from asteroids could be split into hydrogen and oxygen for rocket fuel, supporting interplanetary travel. Metals could be processed into structural components, solar panels, or electronics for space stations and habitats. Some futuristic concepts even suggest orbital factories powered by solar energy, continuously producing parts for megastructures, satellites, or spacecraft. This approach turns asteroids into both mines and production centers, creating a self-sustaining industrial ecosystem in space. One particularly exciting idea is asteroid tugs, spacecraft designed to attach to asteroids and maneuver them closer to Earth or orbiting stations. By repositioning small asteroids, we could simplify mining operations, reduce fuel costs, and ensure safer access. These tugs could also be used to redirect potentially hazardous asteroids away from Earth, combining resource extraction with planetary defense. This dual purpose highlights how asteroid mining technology could serve multiple goals, improving both humanity's security and its industrial capabilities in space. Large-scale industrialization of asteroid resources could transform the solar system into a vast, interconnected economy. Water and fuel from asteroids could support Mars colonies, orbital habitats, and interstellar missions. Metals and rare elements could construct orbital factories, space elevators, and energy stations. Over decades or centuries, a network of mining stations, processing hubs, and transport systems could allow humans to operate independently of Earth, creating a sustainable space-based civilization. The resources are abundant. Scientists estimate that a single metallic asteroid could contain more iron, nickel, and cobalt than is currently mined on Earth in thousands of years. This vision also raises important societal and environmental considerations. Mining in space must be conducted responsibly to avoid creating debris, destabilizing asteroids, or monopolizing resources. International treaties and agreements will be essential to manage rights, responsibilities, and safety protocols. Ethical frameworks must ensure that access is fair and that commercial activity does not conflict with scientific research or long-term sustainability. The goal is a space economy that benefits humanity collectively, not just a few private interests. Asteroid mining could have profound impacts on Earth as well. By supplying rare metals and energy resources, it could reduce environmental strain caused by mining and extraction on our planet. Less reliance on terrestrial mines means less habitat destruction, fewer toxic byproducts, and reduced energy consumption. In addition, asteroid-derived water and fuel could support space-based solar power systems, providing clean, renewable energy to Earth without producing greenhouse gases. In this way, asteroid mining serves as a bridge between Earth's sustainability and humanity's expansion into space. Scientific research remains a central benefit. Mining operations allow in-depth analysis of asteroid composition, geology, and history, offering clues about the early solar system. Organic compounds and water on asteroids may provide insight into the origins of life, while the structure and behavior of these bodies teach us about gravity, rotation, and orbital mechanics in microgravity. Each mining mission is both a commercial and scientific opportunity, blending economic activity with exploration and discovery. Looking to the future, asteroid mining may become routine, much like oil drilling or metal extraction on Earth today. Autonomous fleets, orbital processing facilities, asteroid tugs, and space-based infrastructure could create a self-sustaining industrial ecosystem across the solar system. Water, metals, and rare elements would circulate through orbital factories, habitats, and interplanetary ships, supporting human expansion to Mars, the Moon, and beyond. The dream of a solar system filled with human activity, powered by resources collected from asteroids, is no longer pure science fiction. It is a plausible vision grounded in current technology, research, and investment. Ultimately, asteroid mining represents a critical step in humanity's journey to become a multiplanetary species. By learning to extract and utilize resources from these wandering rocks, we gain materials, fuel, and knowledge essential for life and industry in space. Space elevators, orbital factories, and interplanetary missions all depend on a reliable supply of resources, and asteroids may provide the most abundant and accessible source. They are both treasure and tool, enabling humanity to survive, thrive, and expand beyond Earth. Asteroids, once distant and mysterious, are now being recognized as vital partners in humanity's cosmic future. Mining them responsibly and efficiently could unlock a new era of exploration,